Hello everybody and welcome back. While doing the Mr. to Mega 65 video, I noticed that my promise to do a full color graphics video was already over 3 months old. I guess it is time to finally get this done. First, what is Mandelbrot Explorer 65? It is my plan to make a Mandelbrot generator for the Mega 65 and while doing that, exploring all the features the Mega 65 has, understand how they work and explain them to you. Until now it can only draw one preset Mandelbrot and nothing else. To go on, I first have to explain the basics. The first episode did explain how I had to fix Q opcodes in the core to be able to speed up calculations. This episode will show how to get colorful pixels onto the screen. What graphics can the Mega 65 do? A lot of them, because its Video Interface Controller, or short VIC, can pose as the old and trusty VIC-II that could be found in the Commodore 64. This had already very good graphic capabilities for the time, allowing multicolor graphics in a low resolution using a bitmap mode. The Commodore 65, which was never released, had a new VIC chip, the CSG4567 codenamed Bill, or also known as the VIC-III. It changed in a significant way by making graphics using bit planes like the Amiga does. The Mega 65 can be switched to behave like this, and the closed ROM will use bitplane graphics. As the people behind the Mega 65 are closely tied to the demo scene, they wanted to have fast graphics with lots of colors using less RAM, so they came up with the VIC-IV, which again supports tile-based graphics with lots of colors. This again has different challenges how to organize the graphics in memory, but the DMA Magic chip has some nice tricks up its sleeve to support this. The FCM mode is a character or tile-based mode that allows to use all 256 colors. But this also means that 1 byte of color information is required per pixel, so one 8x8 tile takes up 64 bytes of memory. The trick behind this is that each 16-bit character on the screen is interpreted as a pointer to the flat memory layout of the Mega 65, telling the VIC where to start getting the color information of one of the tiles. The mode allows for a maximum of 8192 unique characters. As an additional quirk, you still can use the default character set mixed with the full color tiles. First, a little bit about my setup. I am using Visual Studio Code on Linux for editing, the Kick Exemplar 65 CEO2 variant to assemble, and Make for build automation. The Mega 65 R3A is connected via a JTAG USB to the PC, so I can use M65 tool to remote control it. What you can see here is the start of a small test program. I will use this instead of the full Mandelbrot Explorer, so I can show you how to start with some graphics without the noise of imaginary numbers. The basic setup is simple. First I need to tell Kick Assembler and VS Code that the CPU is a 45 GSO2. Then I include 2 predefined library files, which provide constants for I/O ports and some macros for commonly used operations. Next you see a constant called basepage, which I set to the high byte of the label the_end+1. This gives me the page directly after my little test program, and I will move the base page to this so I have a lot of addresses I can use, without messing up anything in the 0 page. You will see that pattern a lot. I try to keep everything the ROM could use as it is, so when I exit the program, everything will be as before. The first macro basic 65 upstart will generate a basic boilerplate with a bank and a syscall to start the machine code. After this, the assembly starts. I switch to 40.5 MHz, unmap everything that might have been mapped via the map opcode, and last but not least, do the magic VIC-IV knock. How this is done you can explore on your own by looking at my repository, which is linked in the description of this video. The next 2 macros will move the base page to the constant I calculated before, stop interrupts from happening, and then clear the UART key buffer of any keystrokes that might still be in there. This is a good practice if you plan to use this method of input. After this, after the start label, we begin with the real stuff. And for exiting the software, I will reset the base page to 0 and then return to basic. Let's build this so we can see everything works. For this, I use a simple makefile, which has a target for the PRG, but also has a target called run FCM, which will push the PRG via M65 to the machine and run it. This is very handy because I don't need to build a D81 disk and write it to a SD card. I will now start by typing make FCM test.prg. As you can see, it executes kick-ass and it prints out a lot of stuff it has done. I also like to let it create a byte dump file, which I call FCM test.lst. Looking into it, you can see the stuff the macros created. Scrolling to the end, we can see that the label the end is at 203A. Looking a bit up, we can see that it loads the base page constant as 21, which is the high byte of the end, 20 plus 1. Looks good to me. Now let's start it on the Mega 65 by typing make run FCM. And first I obviously need to show you the Mega 65 screen. Here it is. So now make run FCM. And you see nothing. Well, you see the deload and the run, but then we get the ready prompt. But that's okay, as the program does not do much yet. Let's quickly type list to see the code, which gives us a bank and a syscall. Okay, so we have the basic setup. Let's start with the graphics. I will put all the graphic stuff I want to be reusable in a separate file called VIC-IV FCM.s. At the start, we specify that we want to import it only once. Then we set the CPU to 45 GSO2 and we import the Mega 65 defs so we have access to those constants. First, I like to have the VIC registers I'm going to change saved so that I can easier restore them at the end. For this, I already set up macros I will now paste in. Store state will save a lot of those VIC registers to a specified memory address and after that. And the restore macro will take care to restore those registers in the right order. Because some of them are hot registers which will trigger changes in others. To use them, we need to import the file we created. And then we can start by using those macros. First, the store state, which needs an address to store the state. I will define this again as a constant, which I call VIC state, and then put it at the end of the base page, because that's a convenient place for me. You can also use non-base page addresses in the macro calls for store and restore. And the restore I will put right in the exit. And again, use the defined constant for the address. Because we would not see anything, we also change some simple VIC registers we can see. And the common practice is to change the border and the background color. So I will just add right after the store state a piece of assembly that will load 0 into the accumulator and then store it into the border color and the screen color. So let's check how this looks. So we call again run FCM, which will rebuild the PRG, and push it again, and we see nothing again. But well, yeah, the Mega 65 runs at 40.5 megahertz, so it's probably switching back too fast. So we need something that we can see that the background color is really black. So let's wait for a key press by calling UART wait key. And then we try it again. And as you can see, the program stops and waits for the key press, and we can see everything is black. And when I press a key on the Mega 65, program ends and will switch back to the colors it had before. Wonderful, works. Next step, switch to graphics mode. But first, we need to take a look at the memory layout we will be using. I will explain the developer-approved default bitmap layout, which is the one used in most examples and which the DMA will support. So by using it, you will have an easier time to understand those. The screen is placed at a convenient place in memory and uses 40 by 25 by 2 or 2000 bytes. Graphics will be placed somewhere up in memory, for example in bank 4 or hex 4000. By dividing this by 64 or hex 40, we get a start tile pointer value of hex 1000. Now we will fill the screen with those offsets, doing vertical stripes. So the first column of the screen goes 1000, 1001, 1002 down to 1018. Hex 18 is decimal 24, so 0 to 24 is 25 rows. The next column starts with 1019 and goes again downwards, filling the whole screen column by column with those values. When the VIC now looks at the screen to generate a pixel, it takes the lower 13 bits of this value and shifts its left by 6, which means multiplying it by 64, and uses this as a memory location to look up the first pixel. The first 8 bytes are the first row of the tile, followed by the next row of pixels and so on. As you can see, this gives a rather particular layout of pixels. To go down on the y-axis, you add 8 to the memory location. To go right on the x-axis, you need to just add 1, except if you skip to the next stripe, then you need to add 1600 or hex 640 from top to top. Why 1600? Because it's 64 times 25, which is the memory one stripe requires. So our whole graphics screen will be 320 by 200 and uses 1 byte for each pixel, which is exactly 64,000 bytes or nearly the whole of bank 4. The last bit of memory we need is a part of color RAM, which uses the same layout as the screen and as such also takes up 2000 bytes. Its low byte is full of interesting flags, but we don't need them here, so I won't explain them now. You can look them up in the manual. Especially go to X will take you to Wonderland. The lower 4 bits of the high byte have the color information for normal characters. The high bits again are not important yet. This color will have no effect on our graphics tile pointers and it's only used for normal characters written to the screen. First I will define some constants which point to the memory locations I need for our graphics screen. I will place the text screen just behind the base page, so I zero out the low byte of the end and add hex 200 to this. Graphics are placed at the start of bank 4. And coloram is placed just behind the coloram basic uses at FF81000. To VIC-IV FCM, I will add a macro I already created, which will activate FCM mode by first clearing the H640 and the V400 bits in the VIC-III screen mode register. This makes the screen 320 by 200. Then I set both char 16 and FCLR high and clear FCLR low in the VIC-IV screen mode register to activate 16-bit characters and full color tiles for characters greater than 255, but leave characters below 256 as standard text characters. Next, I will need to tell the VIC that each row needs 80 bytes of memory by setting this into the line step registers. As our rows of 40 characters each have 2 bytes wide characters. And then both screen and color register pointers need to be set to the respective locations in RAM. Note that I only need to set the low word of the color RAM because the bank is fixed. Now I call the FCM Screen on macro with constants for screen RAM and color RAM I defined earlier just before our wait key call. Now let's build this. Well, you see lots of garbage on the screen. This is the uninitialized memory we pointed the VIC at, so we see random garbage. But pressing a key reverts everything, so the store-restore pair still works nicely. Next, we need to clean the screen and set up the pointers to the tiles. First job is to fill the text screen with tile pointers to graphics memory. I need to calculate the current pointer address to graphics RAM, which I would like to store into screen RAM. So I initialize screen pointer with graphics RAM divided by 64, which is shift left by 6. I use the set register to store the offset into the row. Putting 0 there will give me the upper left corner of screen memory. Then we go into the outer loop, where I store the screen RAM address into the screen row pointer. To count the 25 screen rows, I use the Y register. Now we enter the inner loop, where I fill the first column of the screen by storing screen pointer into 2 bytes to which screen row points. I will temporarily increment set for this. Then I increment screen pointer to the next memory address in graphics RAM. As the next row is 80 bytes down, I need to advance screen row by 80. And if we then we decrement Y, and if we did not reach 0, we still need to fill the column. If we have reached 0, we increment set by 2, because our characters are 2 bytes wide, compare it to 80, and if it's not 80, we fill the next column by going through the X loop. And this will fill our graphics memory with all our screen memory with all the pointers to graphics memory we need, as you could see in the diagram I showed earlier. That was the hard part. Now the easy part, filling graphics and color RAM. Easy because we will be using DMA jobs for this. Oh, you don't know DMA jobs? Let's take a look. This slide is a quick reference to the fields a DMA job has. I will be using the extended Mega 65 mode, which adds a zero-terminated option list to the start of the DMA job. The job consists of a command, which mostly will be fill in our case, a word, which is the number of bytes to work on. After this, a source and a destination address, which is 20 bits long each. The upper 4 bits are used for flags. We don't need here. In the case of the fill operation, only the LSB of the source is important, as it is the data that will be filled to the destination. Then the job ends with a 2-byte modulo field, which we don't need. The MSB of the command will not be present, as we will tell the controller to do an 11-byte job. The main reason we use a DMA job is speed. It can fill 40 megabytes per second, and we are only going to fill around 64K. You can skip back to this slide for reference while I do the actual programming, or download the slides from the repo. Okay, I need to clear graphics and color RAM. Let's build the DMA jobs for this. I will be using extended DMA jobs, which have the option list before the DMA job structure. First, I need to clear graphics RAM by filling it with graphics call. This is an 11-byte DMA job. The command is fill, and I will chain another DMA job. Count is 64 times 40 times 25 or 64,000. Source address is the color code to fill with. Destination is the graphics RAM address, which I need to split into the low word and the 4 bits of bank information. The flags need to stay unset, so I mask out the bank nibble. And modulo is set to 0. First job done. Next is the low byte of color RAM, which introduces 2 new options. First, I need to set the high byte of the destination address to FF, as the color RAM is located in the area above 256 megabytes in flat memory. And then I only want to fill every other byte, as I want only to set the low bytes to 0. This can be done by setting the destination skip rate whole part to 2, as this normally defaults to 1. Skip rate is not really the right term, it better should be called increment. After this, the standard stuff follows. Command is again fill and chain, count is 40 times 25. Source is 0, and destination is the color RAM address. Now the last job, which is filling the high bytes in color RAM. This looks nearly the same as filling the low bytes, with the exception that this is the last job, so I don't set the chain flag. The source is this time the color value provided with the macro call, and with the high nibble cleared, and the destination address starts 1 byte later, as we like to fill the high byte. After this structure is built, we can now tell the DMA controller to execute it by writing the start address of our DMA job structure to the DMA address registers. The job is executed as soon as the low byte is written to one of the low byte registers. As I am using extended DMA jobs, I have to use the ETRIC register. Last, I need to branch over the DMA data structure so the program can carry on afterwards. Now I need to add the macro call to the main program right before screen on. In the call, I provide the memory addresses by using the predefined constants and use black for graphics RAM filling and white for color RAM filling. So let's run this and see if it works. And the screen is black. Wonderful. This is what we were expecting. And we can now draw some colorful pixels onto the screen. To write to graphics memory, I will be using 32-bit base page indirect set indexed addressing. So I first need to set the graphics RAM address to a 4-byte base page pointer. Now I will write color codes to the first 256 bytes of graphics memory with a simple set-based loop. For the color, I use the value of set capped to the range of 1 to 4. This should be enough for the small demonstration. The value is stored to the 32-bit base page pointer with set as an index. Kick Assembler uses double round brackets for 32-bit addressing, as square brackets are used for arithmetics. As you remember, this will be very fast, so I add wait key after the pixel is drawn. And I also check for small q, so I can abort early. When set reached 0 again, the loop ends too. Let's run this and see what we get. First pixel is already on the screen, so the 8th key press should give us the first pixel in the next row. So as we go on, you will see after 64 presses, the next pixel drawn is not in the next column, but it is the next character in the first column, which is right below the first character. And so our column of pixel, our 8 pixel wide column of pixels goes down till all of the first 256 bytes are filled. And then the program will end. Nearly there. And that was it. Okay, I now will manipulate the recommended screen layout a bit. So I will set the first character of the second column to the pointer to the second character in the first column. So we essentially have two places on the screen which point to the same graphics memory location. Let's try this. And you see, it looks just the same as before, but as soon as we reach the 64th character, the second column will be drawn at the same time as the first, because it is just the same tile. But only this is the only tile that is affected, and as you see, now it just goes on. We only replaced one of the characters, and this was the first one in the second column. Okay, now we try the Q. Okay, Q works. Now I will add some text, so you can see that the FCM screen still can display characters, as I left the FCLR low bit unset. For this I will add a sample text at the end of the program, which I will zero terminate. And I tell Kick Assembler to use Commodore screen codes to encode the text. Next, I add a simple loop that will read the text until the 0 byte is reached. The writing part will stretch the text with an extra 0 byte after each character, as our characters are 16 bits wide and I need to set the high byte to 0. And last, I will add an up arrow character to the 5th row of the first column, so we have a nice indicator where our 256 pixel region ends. Let's take a look at this. You can see the text, and it is white as we filled the column high byte with 1. And here are again the pixels. And they will reach the up arrow And if it's reached, the program will exit. Just a few more, and this was it. So now we've seen everything there is to see about pixels, but perhaps I add a little bonus content. What about drawing lines? Well, the DMA controller has you covered. Let me add another DMA job to our macro file. So this one will take a start address for the line, a slope and a color. And the DMA job is extended with a few additional options. One tells the DMA controller about the row layout, and another one adds the slope to the DMA job. And then there's one which tells the DMA controller to actually draw a line. And the rest is pretty standard. We fill, we draw 150 pixels and set the color into the source address. And the start address goes into the destination. And this is the DMA job. So save this and then add some calls to this macro with some magic numbers. So essentially you can see that I'm calculating the third row and the third column and the third row where the line starts, and then I use some slope values and ascending numbers for the colors, and after this I wait for key press. So let's try this. Again, we get our screen with the text and we draw some pixels, but we already seen that, so press Q and there are the lines. And as you can see, in the places where the characters are, there are no lines drawn because there is no reference to the graphics memory where the line is drawn, but only a reference to the standard character with the high byte set to 0. So the standard characters blank out in a way the graphics. Well, they don't. Actually, there's just not the reference to the correct graphics style. So we are not drawing characters to the graphics screen. We are overwriting the pointers to the graphics screen and use this to draw characters instead. Okay, I hope this was understandable. Yeah, you can do much more using the DMA controller, but I will let you discover this on your own, because this is part of the fun, isn't it? What did I not show? A lot. As you could see, the DMA controller can work with the special memory layout, being able to draw lines. But it also can do texture scaling, which can be seen in the MegaMaze demo. And there's even more. Try asking about the infamous spiral mode on Discord to get a good story. But there's also more the VIC-IV can do with the rest of the bits allocated by super extended attribute mode. Remember, we are using only 13 bits of the 16 bits of screen RAM and only 4 bits of the 16 in color RAM. You can use raster rewrite buffer to place characters in the row pixel exact over the already drawn characters. How does this sound? A lot like soft sprites, right? There are some demos on your intro disk that will showcase this. You could do really colorful tile-based games or demos with all those features. I think this should have given you a good base to understand FCM mode and hinted you with enough features so you can go and explore. There are lots of examples out there to look at, and you will find folks on Discord who will be eager to explain their tricks, right? I'm not sure yet what the next video in the series will bring, but being able to calculate a sub-region of the Mandelbrot set would be great. I could use some sprites to select the region. And I am planning to explore other cores by trying to port a Mr. core by myself. I hope I could inspire you to explore the features of the Mega 65 on your own. You don't need the hardware to do it. Most of it will be usable in the emulator. So please give it a try. That's it for today. Have a nice time. See you next time. Bye bye.